Okay, so here's my lesson 4.3 on slope. I want to start this lesson by suggesting that this is one of the more important lessons actually that you'll learn in high school, mainly because the concept of slope is something that's really, really fundamental to what we do in actually almost every single year when we're talking about how functions behave and how lines behave. But we'll start off with the basics by just talking about what slope actually means. Some of you who ski or do certain things on the ski slope, like snowboarding, understand what slope is. Like you can have a steep slope or you can have not a very steep slope. That's basically what slope means. It describes the steepness of a straight line. So you can see by my diagram right here that we have a rise and we have a run. So this is our line, this is our hill, and we have a rise and we have run. Mathematically, we can explain slope by looking at rise and run and dividing. That gives us a fraction or a decimal in some cases, and it gives us a whole number in some cases, gives us a positive number or a negative number in some cases. But again, the real key element here is to understand a very, very basic thing is that we mathematicians like to talk about slope in terms of rise over run or rise divided by run. Let me just give you a quick real life example of this. A ladder's base. So a ladder's base is 2 meters away from a wall and reaches 10 meters up the wall. What is its slope? Okay, so again, we're not really talking about Pythagorean theorem here. We're not talking about how long the ladder is. This is our wall, and this is our ladder, right? And our question here says that the ladder's base, that's right here, is 2 meters away. So that's the distance there. And that it reaches 10 meters up the wall. So that this distance from here to here is actually 10 meters. Okay. And so basically, if we wanted to find the slope here, we would basically just take 10 and divide it by 2. So, we would do slope is rise over run, which is 10 over 2. And in this case, the slope is 5. Now, again, this is important. Why? Because then at least the manufacturers of this ladder, regardless of how long or how short it is, can sort of communicate to you what is safe and what is not. So they can say, this is one standard number, 5. Don't go over this number of 5. Don't go under this number of 5. All that types of stuff. Okay, so it just describes the steepness. Now, of course, the question that I'm sure that you're wondering here is what the heck does that have to do with ordered pairs, right? We've been talking about ordered pairs for the past few days. What does that have to do with it? Well, yesterday we looked at how ordered pairs created lines, specifically lines of best fit. These slopes help us understand how these lines behave. So they help us make predictions, right? How much is it going up by or down by each time? And if we know how much it's going up by or down by each time, we can predict what it's going to be in a year's time or whatever, if we're talking about years. Here's a very simple illustration. So I'm going to pause my video right now, and these points should pop up in just a second. Okay, so what's neat is I just paused it and restarted, but I've got these points plotted now. So A, B, O, C, and D. So actually, if I wanted to calculate the slopes of AB, so again, AB is just a line segment, right? It's just a line segment between A and B right here, right? These 2 points. If I wanted to find the slope of that pink line that I just drew, I could look at the rise over run from A to B. So, what did I rise by to get from A to B? Well, I rose 2 squares, actually. Like, I went up from here to here. I rose 2 squares, and I ran 1 between B and the actual endpoint. So my rise over run is actually going to be, 2 over 1. And 2 divided by 1 is just 2, right? You can bust out your calculator and find that out. CD, in a very interesting sort of similar way, right? Between CD, an interesting thing happens in that if I look at my rise again is 2, and my run again is 2. That's pretty neat, because if you think about it, right? There's something interesting about all of these points. Rise over 1, run 2 over 1, that's 2. DB. Well, what about DB? Here's something interesting as well, right? Like, let me clear out the clutter here. These rise out of runs out of the way, or over runs out of the way, and we get a look at D and B. So the line segment that connects D and B is interesting as well, because its run is actually negative. Right? Between D and B, we go down. We go down 1, 2, 3, 4, 5, 6 squares. So we have a rise of negative 6, because we're going down 6. And we actually have a run of negative 3 as well, because if you think about it, we're running in the negative direction towards the left by 3 units. So it's actually negative 6 over negative 3. And that actually winds up equaling, positive 2 again, because a negative divided by a negative is a positive. So this is something that's actually kind of interesting about all the lines, or all the points and all the slopes that we've been talking about today, is that all of these points are actually in one straight line, right? What's the line of best fit? Well, the line of best fit for all these points is a nice straight line that goes from D to A. It could actually continue further on down if we really wanted to, right? It can continue in that direction and in that direction. But if you think about it, it's a perfectly straight line. It's not just the line of best fit. This is actually the line that models those particular ordered pairs. And you can actually see again that the slopes are always the same because it's rising and running by the same amount each time, regardless of which 2 points you are talking about. We can also find the slopes or the steepness without graphing. Now, the reason why that's advantageous is because, well, graphing, we need graph paper, we need rulers, we need to do it in pencil. What if we miss? What if we draw it in the wrong spot? What if we miscount? Right? A bit awkward. We're going to use a graph as we do 2 of these, but we're also going to calculate it what we call algebraically. That means just using numbers, adding, subtracting. So we see up at the top here this really, really useful equation, something you might want to commit to memory. So when we're talking about the slope, we're actually talking about delta y. Now, delta is a Greek letter that represents the change in. So the delta y represents the change in y, and the delta x represents the change in x. So how much y changes by? Well, how do we figure out how much y changes by? Well, we just take the second y value, in this case 8, and we subtract it by the first y value. So we would get 8 minus 2, right? That is y2 minus y1. We would then take the second x value and subtract it from the first x value. That tells us how much x is changing by. I don't want to use a yellow pen here, so I guess I'll use, I don't know, black. So we'll divide that by 3 minus 1. The slope of these 2 points, again, should be 8 minus 2, which is 6. 3 minus 1, which is 2. That should be the whole number 3. Now let's take a look and see if that's true, okay? Let's plot these points. So again, based on what we learned the other day, positive 1, positive 2, that's where the first point is, 3 and then 8. So positive 3 and positive 8. There it is, right? So check this out. So these are your 2 points here, right? So your rise and your run. Well, your rise is actually 6 squares, and your run is actually 2. That's why we got this 6 over 2 business going on here, right? So if we wanted to actually talk about the slope between these 2 points, that's this pink line that I've just drawn here, the slope of that pink line that connects those two is actually 3, because its rise is 6, its run is 2. 6 over 2 is 3. I'm okay with that, hopefully. So let's plot 2 more points. Let's talk about the 3 and then 4. So 3 and 4, so positive 3 and positive 4, that's right there. And positive 2 and negative 1, so positive 2 and negative 1. There's these 2 points here. So again, if I was to sort of model this slope with the pink line, that's what it looks like. Well, what's its rise? Well, you could count the squares if you really, really wanted to, or you could do this algebraically. So again, let's do this algebraically. Let's take the second y value, which is negative 1, and subtract the first y value, which is 4. Let's divide that by the second x value minus the first x value, which is 3. So that, a little squiggly line to divide my work here, that should actually equal negative 5 over negative 1. A negative divided by a negative is a positive, so that winds up being positive 5. That's also illustrated by these 2 green lines. If you think about it, this is a rise of either positive 5 or negative 5. If we're going to count it as negative 5, it means that we're going from this second spot down 5, which means we still have to go actually down 1, or to the left 1, horizontally. So its run is negative as well as its rise, or they're both positive. Okay, so that's what's actually kind of interesting about this example. Remember I said, though, that slopes could be positive or negative. So let me just quickly, suggest that, right, we could be talking about 2 points that give us a slope that looks like this, or 2 points that give us a slope that looks like this. If you think about it, the rise here would be negative, but the run here would be positive. So an interesting thing about this particular question, right, is that we have a negative slope if those were the 2 points, right? Didn't choose those in my example. So anyway, that's slope in a nutshell. Tomorrow, again, we'll pick this up as a concept. Remember, though, that slope can be described in 2 ways. It can be described as initially rise over run, and it can also be described as this delta y over delta x. So if we're talking about ordered pairs, delta y over delta x is what you're going for. If we're talking about just a real life situation, a ladder or a ski slope, we're probably going to talk about rise over run.